So, hello everyone, and thank you for having me. And today, I want to talk about something about KAI HPC implementation, which is Korean AI foundational model building, and we built the system on it. So, let's get started. So, let me start with the macro trend. We are entering a period that the AI is bubbling and computing demands can grow by roughly 4 times a year. And this means the amount of computation method needed to state-of-the-art models, training, and the inference is exploding. But our infrastructure, data centers, power, storage, networking, and operation systems does not scale at this time and at the same pace. I mean, the scaling budget is going higher, but the offline real computational resource does not scale out like this in this pace. So this is the core infrastructure dilemma of the AI era. Demand is compounding, but the capacity, budget, and human expertise are not. So our organizations are being stopped. Do you overly invest in hardware and hope to catch up? Or do you live in the chronic bottlenecks, underutilized GPUs, and unstable environments? The gap between the AI workloads needs and what current infrastructure can deliver is widening, and there is some problem space we are addressing. So to understand why it's so hard, so we should look at the problem beneath of it. So these are lots of problems like if this infrastructure is getting wider and wider, there's a bottleneck, lots of bottleneck, like interconnect bottleneck and utilization efficiency and other cooling features and schedule problems and data loading problems, and even the electricity can become the problem. When the technical depth is combined with the physical constraint of AI data centers, power, cooling, spaces, and network throughput, you can get systems that are fragile and hard to debug and very expensive to operate. What we see in practice is the day-to-day operation challenges of running AI workloads. They often keep job running and managing failures and upgrading softwares and recognizing the needs of many teams and models on finite resources. So the first big category of pain is cost and power. GPUs themselves are extremely expensive. At the same time, they consume enormous amount of data and energy. If your data path, storage, and network I/O is not fast enough, the total training speed is slowed down, and your GPUs are going still idle, and your actual cost per use per token explodes. On the power side, I think in the electricity, we are going to trans to rack to be used. One rack was used to be 4 kilowatts per rack, but nowadays the rack requires more than 200 kilowatts per rack. So in this case, the previous existing method on traditional consumption patterns were not suitable for these AI workloads. So you have the expensive hardware that is underutilizations and power that is stretched to the limit. And this is not sustainable. And we need a way to dramatically improve the efficiency, not just add more GPUs. The second big category is complexity. The new model AI are being released every day, like this. Currently, over 1 million AI models are registered on Hugging Face, and even now, the new models are released every day, and models downloads are more than 1 million times a day. And recently, Hugging Face released that they download are more than 15 petabytes per day, so that amount is very enormous. And even the framework like VLLMs and like TensorRT models are bi-weekly released, and this pace is very thick, and very hard to follow up. For the infrastructure teams, this means that you are constantly chasing a moving target. The combination of exploding those situations, frameworks, versions, and drivers and accelerators, even the accelerator from not only from the NVIDIA, but also from the Intel and Google and the other NPU storage are exploding too. The single incompatible version like mismatching a driver version or mismatching a program version or a kernel version can make an explosion or conflict, and or making it could be running, but it could slow down more than 50% of total utilizations. So AI workloads is different from the existing workloads like simple web version or deploying some service workloads. So the AI workloads depends on this zero output, and resource efficiency is crucial. So before the AI, the existing workloads were recast based on the recast. In case of the web, the request latency and availability was the highest demand. But in case of AI workloads, the total GPU price is so high, so the utilization is more important than the other resources. So the key metric is the GPU utilization, and you have to concentrate on GPU-centric things like you have to make the GPU to work as much as possible, like making a network bandwidth or I/O bandwidth to make two GPUs to work harder, and not to make it in idle mode. So you have to use storage to GPUs like fast data and high-speed networks like RDMA and careful tunings to. And also the environment management becomes more sensitive. In case of small variation could be catastrophic failure, and even the small kernel version update could make the failure. By contrast, the existing workloads was typical web service, like CPU-centric and short-lived, and it could be stateless. And yes, that the GPU version is very stateful, and this previous existing stateless method cannot cover these AI workloads too. So how do we respond? So our approach is on the lab is transforming GPU complexity into the operational simplicity, primarily through using the software. There is a simple principle that called our design. So the maximum performance depends on your hardware. If you buy more DGX machines or HGX from the NVIDIA, then the maximum performance is getting higher. That is so trivial. But the maximum efficiency is determined by not the hardware, but from the software. At this moment, if you use the raw hardware and benchmark using ML flows, you can get the maximum flows in there. But if you try using PyTorch and using some Nematron or something like Megatron LM to training or large language models, then the efficiency becomes a crucial point, and you can find that the maximal MFU is just around the less than 45% of the total promotion GPU performance. So what does the software-defined AI structure look like in practice? First, it increased overall resource utilizations, including GPUs and of course CPUs and storages and RAMs, while reducing wait times and therefore reducing cost. Instead of idle GPUs waiting for jobs or jobs waiting for GPUs, the system continuously optimized the placement and scheduling. Second, it should simplify the learning and development through the recipe and standardized environments. Team can focus on model and data and training codes, not the rebuilding the training environments at the moment. Third, it connects the full MLOps pipeline, training and inference, across a consistent platform. This includes the hardware virtualization and abstraction, and AI workload-centric scheduling and environmental standardization. And finally, it supports a high-speed storage and faster data I/O in the first-class consensus. In other words, the platform engineered around the real bottleneck of AI workloads not only near the assumptions from the traditional cloud computing. Okay, so to go around in something concrete, so let me share the application in real KAI foundational model. So initial project in this project was called World Best LLM. In this project, they do not support money. Instead, they provide a GPU resources to the several teams and to grant them and them use to GPU clusters and making the LLM model themselves. So the program started with 5 continuous SOCIA, evaluated with every 6 months, and gradually narrowed down team to make the final 2 teams to make a year of support. The library participate in offstage consortium and providing our backend programs are there. So you can think there's a real-world data center, and they set up by GPU cluster by SKT, and we install the backend AI workload management on the surface of the GPU cluster. And offstage researchers are training jobs and running batch scheduling, like using Torch Titan program on our backend AI platform. So they're training a 100 billion size pair of MOE architecture models, and we are currently using 500 full GPUs to 63 GPU nodes. So not the all. Of course, it is very useful if we use the total 500 GPUs for training. But in case of the GPU failure that is happen all the time, we need to set up backup nodes for it. So we set 60 nodes for training and 3 nodes for testing and for the backup. And we use fast eBox storage for 2 petabytes for fast storages. And we currently using PyTorch 2.9 nightly version and Torch Titan 0.2 version in development live main branch. And we're currently using CUDA 13.0 and Nickel 2.28.3. Currently, this work was required is since we are training on very large scale models, and this project has a time limitation, so we have to focus on the maximizing GPU workloads availability for this project. So even a single GPU hardware configures, then every GPU cluster will stop. And of course, you can think like this: what about just stopping and rerun the job scheduler by human? It is okay, but for user moments, but that is not option for ours. It should be run automatically and as fast as possible. So what happened in reality when you're training on more than 500 GPU cluster for a single job? So this is a real GPU user cases, and this is a power advantage from DCG and NVIDIA. But there was a lot of issues for this training. And currently, the job is still running, but there was several issues like NFS mounting issues. Sometimes suddenly the GPU cluster, not only GPU, but also the CPU nodes shut down, and they are losing NFS mount. And sometimes GPU are losing themselves. If you're typing NVIDIA SMI on nodes, and sometimes it should have 8 GPUs, but sometimes it just shows 7 GPUs at all. And it means the single GPU got forgotten and somewhere, then the total job can fail at all. And the most confounding issue was nickel issue, and NVLink issue was also over there. And sometimes NVLink and InfiniBand goes down and die sometimes. Nickel version issues were over there, also there, and we have to update the Nickel version to the latest version as much as possible. So, and there was a storage performance degradation issue that we're training data with Hugging Face dataset library to load data from the fast data storage, but we split data to 500 megabyte size to load from the large scale of distributed data sets. But when we are using memory mapping method, they read over metadata from the storages. But when we are loading real data, the GPU cluster should read those 500 megabytes data per file, but they they failed to get the data because there were some several bugs in the NFS driver bus, and we fixed them via the collaboration with the VAST and GPUs too. So this point, this is where the backend AI is called the workload and infrastructure manager for the GPU cluster. We implemented a batching-based scheduler designed to optimize a single, very large job across the tens to thousands of nodes and hundreds to hundreds of containers. When a calculations kind of training session fails, then the system automatically restarts the containers and attempt to reschedule without human intervention. Monitoring and alerting are integrated with tools like Grafana and DCGM, and we focus on making provisioning tasks so they can safely retrieve. So we also use MLOps tools like to make workload restarts, and we use Luna scheduler to support the unique CPU thread into pass through with the virtual machine environment. All of these tools together allows the cluster to scale out without intervention or while preserving stability and for efficiency too. So even with the strong orchestrator, it requires several other issues too. Okay, so for example, previous example, we encountered storage data loading performance issue when the training data was played with the 500 megabyte chunks, but the root cause turned out that the mismatch NFS drivers MF-related overhead, which is split 500 megabytes one request to the 4 kilobytes of thousands of requests. So the requests the network were overheated to the most enormous request, not the real data consumptions. And also, we saw performance and stability issues with NXLP8 processing in a Blackwell GPU's environment. And at that moment, we discussed with NVIDIA and solved the driver issues and updated for it. On the network side, we optimized ROCE and InfiniBand, diagnosed that NTU mismatch, like MTU count were different from the host size and the other container size, and it makes the degradation of network switches. So we tried a countless of nickel options and MTU optimization options to minimize the idle of GPU times. So the key takeaway is here that delivering reliable and high performance of AI at this scale requires close collaborations between the data centers, the GPU vendors like NVIDIA, and server providers like fast storages, and model developers like Upstage, and infrastructure manager like us. So this is the real backend AI platform screenshot that runs on 580 GPUs at the moment. Okay, so let me zoom out and show how is structured the overall AI stack on level. At the bottom, you have the data center and power, cooling, location, backbone network, GPU, accelerators, interconnect network like InfiniBand or high-speed internet. On the top of physical layer, we call it on AI Infra OS, where this is on backend AI operates as a reservoir of the computing resources, preventing a unified API and management layer. Above that, we have orchestration and ML AI ops components, like Kubernetes Swarm, MFO, like CUDA and Nickel, GDS, and data bubbles like Fast Track. So we have several monitoring tools, and so that we can cover all of these systems using our level of backend AI platform. So, and all of these efforts are guided by 3 principles. First, make AI accessible. And second, make AI scalable. And third, make AI composable. So the software-defined AI structure with KAI implementation is now based on our principles. And So this is for my presentation, and thank you for coming. And if you are interested in our backend AI platform, please visit our demo booth, and we are prepared for several events, so please join our events too. Thank you.